Hey, this is quiz review for sections 1.2 to 1.3. So you were given a piecewise function and you're asked to find the value of the given quantity. So part A, find f of negative 7. So we're simply looking for the ordered pair on the graph. So if we go to negative 7, we see that the y value is at 4. So f of negative 7 is equal to 4. F of negative 6, again, we're looking for the ordered pair. So at negative 6, there's a vertical asymptote that's affecting both branches on either side. However, we're only looking for the ordered pair, and there is an ordered pair that exists at y equals 4, or at the y value of 4. So that's our y value for f of negative 4. Limit as x approaches negative 6. So we're looking for the behavior of the graph going towards x value of negative 6. And we see that as we go towards negative 6 from the left side of negative 6, we see that the y value is approaching positive infinity. As we approach negative 6 from the right side of negative 6, we see that the graph is approaching negative infinity. So we can't say that both sides is approaching positive or negative infinity. So the most we can say is that the limit does not exist. Limit x as x approaches negative 2. As we approach negative 2, we see that the left branch is going towards positive 3, but the right branch is approaching negative 3. So we see that the branches do not meet at the same y value, so we can say that the limit does not exist. Okay. Limit as x approaches 2. As x approaches 2, we see that the graph is connected towards a specific y value, and this y value is negative 7. F of 2, we're looking for the ordered pair, so f of 2 is 1. F of negative 2 is just the ordered pair, negative 1. And then limit as x approaches 6, we see that the left branch is approaching a y value of 3, but there is no right branch. So what that means is the limit is not going to exist because we don't see anything on the other side of the graph. The graph has to connect to the same point from both sides of the target x value. So here the limit does not exist. Identify values of c where the limit exists. So limit is going to exist in this region, and in this region here. So we identify that from negative infinity to negative 6, but there's an asymptote there, so we have to consider a break from negative 6 to negative 2, but the limit is not going to exist at negative 2, so we have parentheses, and then from negative 2 to positive 6. However, we can say that the limit exists here, so we can have the graph, the domain exists from negative 2 through positive 6. Okay. Number 3, you're given 6 characteristics, and you have to create a graph based off of these 6 characteristics. The easiest ones to start off with are the ordered pairs. So f of negative 3 is equal to 1. We can just plot that point. F of 2 is equal to 3. Plot that point. F of 6 is equal to 5. Plot that point as well. So now we can take care of the limits. Limit as x approaches negative 3 is negative infinity. So we want the graph, both branches of the graph, to go down towards negative infinity. Limit as x approaches 2 is equal to 7. So we want the graph to connect to the y value of 7, even though the ordered pair exists at 2, 3. So the graph, the ordered pair exists at 2, 3, but we have the limit, the graph heading towards the y value of 7 from both sides of the graph. And then finally, the limit as x approaches 6 does not exist. So here I just have the graph stop at 6, 5, and I just left it there with nothing on the right side. Now it's possible that you could also have another branch that continued on the other side. But as long as you don't have the graph connect to the same point, this also is acceptable for where the limit does not exist as x approaches 6. So you can leave this branch out, or you can have this branch here. Either way would fulfill the sixth condition. Okay, evaluating limits algebraically. First thing we do is we always plug in the target x value. So if we plug 3 in, we're going to get 0 over 0, which means that we can continue with the problem. So we can actually find the common denominator and within this complex fraction. We can factor the 2x squared minus 5x minus 3. We can simplify and combine this complex fraction, and we're going to see that the x minus 3 cancels out, which leaves us with 3 over 2 times x minus 1 times 2x plus 1. So now that the x minus 3 is canceled out, we can re-plug in our argument, and we're left with 3 over 2 times 7, which is 3 over 28. Okay, number 5, first thing we do is we plug in our target x value. In this case, it's going to be 0. So when we plug in 0, we're going to get 0 over 0, which means that we can continue working with this problem. Here, we can multiply by the conjugate of the numerator, which is root x plus 16 plus 4. And once we do that, we can expand. Expanding will leave us with x plus 16 minus 16, all over 2x times root x plus 16 plus 4. And then the numerator reduced to be just x, which will cancel out with the denominator. And then once the x goes away, we can re-plug in the 0 and for the remaining x. So 0 plus 16 is 16, root 16 is 4, 4 plus 4 is 8, 2 times 8 is 16, so therefore our fraction is 1 over 16 is our limit. Okay. Number 6, first thing we do is we plug in the 2/3, and it's going to allow the numerator and the denominator to be 0 over 0, which means we can continue working with trying to factor and finding common factors. So the numerator will give us negative 5x plus 2 times 2x minus 3. Denominator stays as 3 minus 2x. We cancel out the numerator and denominator. However, the 2x minus 3 requires us to factor out another negative, which cancels out with this starting negative. So we're left with just 5x plus 2 with the other factors canceled out, and then replace x with 2/3, and we get 10/3 plus 6/3, or 10/3 plus 2, which combines to be 16 over 3.